Throughout this training, or at any time you need support, there are many ways to contact us. You can follow us on all major social media platforms or email us directly via our website, or you can click the Cancel Connect icon shown at the bottom of this slide on our website to book a consultation with one of our experts. When we collect data and analyze data on an entire population, it's called descriptive statistics. Whether we're counting grapes in a vineyard, people, marbles, or windshields, the population is the entire group that we want information about. And if we study every single unit in that population, it's descriptive statistics.
The alternative to analyzing an entire population or every possible unit or piece of information is sampling. In statistics, a sample is an analysis of just those parts that we choose to represent the whole. When we gather a portion of the population or sample, we use the sample data to draw conclusions about the entire population. This is called inferential statistics. Inferential statistics means that we are inferring a conclusion or predicting using a subset of the data. So descriptive statistics is based on studying a whole population, and inferential statistics draws conclusions based upon a sample.
Sample size is a frequently used term in market research and statistics, and one that inevitably comes up whenever you're studying a complex process with huge numbers of units or transactions. So why does sample size matter? When you study a large population, you're interested in the entire group, but it may not be realistic to get answers or results from absolutely every unit. In the case of our vineyard here, that would mean analyzing every single grape or every single leaf. So we take a sample which represents the population as a whole. And how well we take that sample will determine how closely our analysis represents the whole.
The size of the sample is very important for getting accurate, statistically significant results and running your analysis successfully. If your sample is too small, you may miss critical characteristics or information. These skew the results, and you don't get a fair picture of the whole population. If the sample is too big, the whole study becomes complex, expensive, and time-consuming to run. And although the results may be more accurate, the benefits don't always outweigh the costs.
Sampling is a critical technique for any business and process improvement team. For example, in manufacturing, when a truck pulls in loaded with raw materials, the receiving department must decide whether to accept the shipment. From their point of view, a truckload of about thousands of pounds of grapes is the population. The inspectors can't look at every grape to make sure that they're good, and even if they could, it would likely produce too many mistakes due to human error. The inspectors can get better information by studying a 100-pound sample taken by filling buckets at 5 different points down the length of the truck. Then all along the process or production line, workers continue to take samples to ensure that the winemaking process stays on track. If we wait until the end of the process to inspect only the finished product, problems that were minor to begin with could be greatly compounded. Instead, sampling at key points catches problems early before they get out of control.
For our conclusions to be valid though, the sample must be representative of the entire population. To make sure that it is valid, we rely on what is called simple random sampling. That means the sample is chosen in such a way that each individual has an equal chance of being selected. This helps to eliminate bias in the data. For example, if we are studying wine grapes and we only choose those that are easily accessible on the top of our barrel, the sample wouldn't be representative of the whole population, because we would be likely to overlook grapes at the bottom. A truly random sample ensures against non-representative or biased results, allows each and every unit in a population or process an equal chance of being selected in the sample, and provides sound basis for doing statistical analysis and drawing correct conclusions.
Most DMAIC projects will involve drawing conclusions from a sample and analyzing that small but important amount of data. So how do we know if we need to sample versus studying the whole population? Before we get to that decision point, let's go over a couple of definitions. One type of population cannot be counted. For example, the total number of fish in the ocean, it's unknowable. Or people in the world, or a number of leaves in a forest. This is called an infinite population. It can't be counted, it's unknowable.
The other type of population is a finite population. It has clear boundaries and is countable or knowable. For example, fish in an aquarium, customers in a region, leaves on a plant. A finite population has clear boundaries that distinguish this group from other groups. This brings us to two types of data collection. Complete enumeration, the official term for studying an entire population, versus sampling.
Of course, in practice, it may not be possible to collect information on all units of a population due to various reasons, such as it's an infinite population, or there might be a lack of resources in terms of money, personnel, or equipment. Another reason for sampling is that collecting data on the entire population may be wasteful if it's not collected within a time limit. For example, a business that deals with hundreds of thousands of transactions every day may have access to the entire population. However, the amount of time it takes to ensure that that data is accurate and that it syncs up across multiple systems may take so long that the results are outdated by the time the analysis is done.
In these scenarios, sampling is preferred due to the time and resources to collect and analyze the complete population. Sampling will be less costly, and many times it is more accurate than complete enumeration.
So the two questions we have to answer are: first, is the population infinite? If yes, sampling is the only way to study the data. The second question requires that we have an idea of the time and resources required to gather the data. What steps are involved? What expertise is needed? Does the data have integrity issues that need to be addressed? If the time and resources to study the complete population are too high, sampling is a great option.
There's no one way to calculate the minimum sample size. There are many variables and factors involved, and there are many tools available. You can find thousands of sample size calculators online. Many of these calculations are focused on surveys and market research. However, they can be very easy and quite useful. Or alternatively, if you are using a statistical software such as Minitab, they include functionality that will help you to easily perform these calculations.
Regardless of the method that you choose to determine your minimum sample size, it's important that you understand the different factors involved. None of the calculations use every factor, but they each use some. So let's take a look at the most common factors that you need to understand to get to the main point, and that is, what's the minimum amount of units that we need to sample to provide us with enough data for us to draw accurate conclusions?
Exactly how lazy can we be and still rely on our data?
There's the question.
We will now walk through the most common factors used to calculate the minimum sample size. These factors are margin of error, confidence level, population, and estimated proportion. And just in case you're curious, in your workbook, you will find the formula used in this example. You are not required or expected to memorize this formula. Well, not by us, but maybe by your company. It's included for reference only for those of you who are interested in what's going on behind the scenes.
The first factor that we'll cover is the margin of error. Sampling errors are to be expected. The question is how much error you'll allow. The margin of error is also known as the precision. It's noted by a lowercase d in statistical equations, or the confidence interval. This factor identifies how many percentage points your sample results may differ from the real population value. If you've ever paid attention to a political poll, you've seen a confidence interval and how it's expressed. It will look something like this. 56% of voters said yes, with a margin of error of plus or minus 5%.
If you're lucky. Let's say that we're studying vines in a vineyard to see what proportion are diseased, and we set the margin of error at 5%. If our results showed that 25% of the leaves are diseased, we can be confident that between 20, that's with 25 minus the margin of the error, and 30, 25 plus the 5%, would actually be diseased. So in this example, our margin of error is 5%. This means that the range of plausible values for our sample results is 10%, from 20 to 30%. That's the confidence interval, or plausible actual results.
To get a tighter precision, or a smaller margin of error or confidence interval, we would need to collect a larger sample size given the same population. That's why political pollsters wait until it gets closer to elections to tighten up the margin of error. It's because the stakes are higher, and it's worth the effort to get a more accurate result.
Now let's talk about confidence level. This is a separate variable to the sound-alike confidence interval, which we just discussed. Confidence level deals with how confident you want to be that the actual results falls within your margin of error. The most common confidence levels are 90% confident, 95% confident, and 99% confident. Just as you need to know your margin of error, it's also helpful to know how much confidence you can place in the results. Do you need to be 99% sure you have the right average number of diseased plants, or will 80% confidence be sufficient for your purposes? For those working on projects relevant to safety, security, or legal, for example, a higher confidence level is usually needed. On the other hand, projects where safety is not an issue, or where the risks and benefits of a greater confidence won't have much impact, we can require a lower confidence level. Just keep in mind that the higher the confidence level you want to have, the larger your sample size will need to be.
What's the total size of the population from which you are sampling? It's easy to think of the population when you're studying people. If you were studying a sample of people across the US, then your population size would be about 317 million. Similarly, if you're studying employees in your company, the size of the population is the total number of employees. In statistics, the term population can have a slightly different meaning. It doesn't refer only to people, for example, the population of Britain, or animals, for example, the wild dog population of Australia. Statisticians also speak of a population of objects, or events, or procedures, or observations, including such things as the quantity of alcohol in wine, number of visits to the doctor, number of surgical operations, or complaints received via social media. A population is an aggregate of people, animals, units, and so on. The sample size doesn't change much for populations larger than 100,000. So if you're not sure, or if your population is infinite, you can use 100,000 as a default.
The next factor, the estimated proportion, is not as common as the other factors. In other words, you may not see this in too many online calculators, but you'll still need to understand what it means and how to use it. The estimated proportion is used when you have a discrete measure with two options. For example, defective and non-defective. Like our product or didn't like our product. On time and late. This factor asks you to estimate how much of what you are looking for actually exists. For example, if we are studying defects, what is the estimated proportion of units with defects? If you have a pretty good idea of what the proportion is, you can guesstimate it, or you can pre-sample. Pre-sampling means that you gather data until you have found at least 5 items that have the characteristics you are looking for. For example, late or defective. And at least 5 items that do not have the characteristics. Then you can calculate the proportion and use that number as your estimate. Or, as a default, you can use 50%.
Most online calculators are made to support surveys and assume that we're using discrete data. So you may have to work around this if you're using a continuous measure. The alternative to estimated proportion when we're using a continuous measure is the estimated standard deviation. Same exact concept here, but we're estimating the variation in the measures that are being studied. If you think about it, the smaller the standard deviation, the less variation, right? That means that the smaller the variation, the more homogeneous or consistent the data in our population, and the smaller the sample size needed. The larger the variation, the larger the sample size will need to be. Many people think that the population size is the biggest factor in calculating sample size, but variability is actually an even more important factor.
So similar to our discrete data, we have two options to find this info. We can guesstimate it, or we can pre-sample at least 30 units and then calculate the standard deviation. When we pre-sample, we have to be very careful of biases. In other words, we need our pre-sample to be an accurate reflection of reality. With these factors in place, the calculation can be completed. This is the minimum sample size you need to estimate the true results with the required margin of error and confidence level. Now let's see what happens to our minimum sample size when we move some of these factors up or down.
If we tighten up the margin of error to 1% instead of 5%, we're saying that we need to be extremely accurate. With a 1% margin of error, our minimum sample size is almost 9,000 compared to the 383 with a 5% margin of error. Let's look at the confidence level. If we loosen that up to 90%, our sample size goes down a bit. It goes down to 270 from 383. So in this case, it might be worth it to go for a bigger sample size if it gets us to 95% confidence.
Now let's look at how the population size affects our sample size. If we reduce our population to 25,000, it barely has any impact on the sample size. And lastly, let's play with the estimated proportion. Our original example estimated that 50% of the population has the characteristics we are looking for example, defects. If we reduce the estimated proportion to 10%, our sample size goes down to 139.
Okay, we've covered the main factors needed for you to calculate the minimum sample size. Let's walk through a few more considerations for you to finalize your sampling plan. In some cases, there are multiple groups in your data. For example, multiple regions, multiple types of customers, multiple types of products. Stratified sampling allows us to obtain a sample that best represents the entire population by dividing it into subgroups called strata. We do this to ensure adequate representation from all types or groups being sampled. In this case, we can perform a sample from each group. For example, in our vineyard, if we want to study 3 different types of grapes, we could take separate samples from our red, green, and black grapes separately to ensure that we gather data that represents all 3 groups.
Now let's talk through an example. We are performing an analysis on our vineyard and we want to ensure the random sample size best approximates the whole population, including grape color and location. Let's say that we have 1,000 clusters of grapes, 2 colors, green and red, and 2 locations, east and west. The total population in the study is 1,000 clusters of grapes, and from there subgroups are created as shown in your workbook.
We would assign every cluster of grapes to one of 4 subpopulations: red east, green east, and red west and green west. Next, we would count how many clusters from each subgroup make up the total population of 1,000 clusters. From there, we calculate each subgroup's percentage representation of the total population. So the subgroups we have are red east, 450 clusters. So out of 1,000, that's 45% of the population. Green grapes in the east location, 200 clusters, or 20%. Red west, 200 clusters, 20%, and green west, 150 clusters, or 15%.
This example makes it easy. Red, green, east, and west are clearly defined groups. In other situations, however, it might be far more difficult. So stratified sampling is not always the best option and can sometimes be an ineffective and less than ideal method. There are 2 major strategies for sampling: random and systematic. Random sampling means that every unit has the same chance of being selected. You can use a random number table or random function in Excel or other software. We have to be very careful when planning for a random sample. It's not always easy to be truly random. A real random sample is one in which every item in a population has an equal probability of being selected.
Systematic sampling is the most practical and unbiased in a situation where we're studying a unit over time. Systematic means that we select every nth unit, for example, every third unit or every fifth unit, or we can take samples at specific times of the day. Our last consideration is the subject of bias. There are many opportunities for mistakes when using a sample. The most common are self-selection. This is mostly related to surveys or polls, but refers to gathering data only from those people who decide to respond. Self-exclusion is the opposite of self-selection. It refers to individuals or groups who can opt out of the sample.
Missing key representatives is another common mistake and happens mostly because of convenience sampling. It can be tempting to collect the data that is readily available, but that doesn't mean that it represents the whole population. Ignoring non-conformances is what occurs when people reviewing the data get rid of the data points that don't look normal. Many times they use the word outlier incorrectly and assume that the data is not valuable. This is probably one of the most common mistakes that we come across, eh?
Yeah, for sure.
With systematic sampling, a risk of bias can arise. However, when the timing of the sample matches a pattern in the process, for example, if we take our sample at the beginning and at the end of the workday, it might be the least busy time of the day, which would not be an accurate representation of the whole process. The point is to be aware of a possible bias in your data collection plan and to take appropriate measures to ensure that the work you are doing will create reliable results.
So we've covered the factors needed for you to successfully determine your minimum sample size, the margin of error, confidence level, population, and estimated proportion. And we've discussed the final steps to complete your sampling plan. That is stratified sampling, random or systematic, and methods to avoid bias. Of course, you may run into more complicated scenarios with your particular project, and if you have anything more complicated than you're equipped to handle, that's when you should reach out to your black belt, or if you have one, or you can always contact us and we'll be there to help. Well, you did it. You made it through some of the least popular lessons in DMAIC, and you did great. Take a few moments to review your notes and get ready for a quick quiz on this chapter, sampling.
It has been our sincere pleasure being with you through this part of the training, and we thank you for your dedication to creating a better workplace and an environment that you can truly enjoy.